In this video, I'm gonna continue to go over 7.4.2 maximum likelihood estimators. Okay, so so today we're gonna see example 7.11 normal distribution of the maximum likelihood estimators for population parameters mu and sigma square. So example 7.11. Okay, so the normal distribution of mu and sigma square. So the script n represent normal distribution. Okay, so we want to find out maximum likelihood estimator of mu and sigma square. I mean mu hat and sigma square hat. Okay, so the PDF, the f of x, okay, and then comma mu and sigma square. So this is defined by 1 over and a sigma and a square 2 pi. I think you can just mention just sigma instead of sigma square. 1 over sigma square 2 pi and the e to the minus and then x minus mu and square over 2 sigma square. Okay, that's the definition of the PDF of a normal distribution. So then maximum likelihood, likelihood function L of mu and sigma square is going to be pi I goes 1 and through n. Here we assume that what we got a random sample of size n. Okay, so under that assumptions, so we could construct the likelihood function L. Okay, so 1 over and then sigma the square root 2 pi and the e to the minus xi minus mu and square over 2 sigma square. Okay, so now this is equal to then the 1 over sigma square root 2 pi and to the nth power and the e to the minus 1 over 2 sigma square and then the sigma I goes 1 through the n and then xi minus mu. You understand that? You see that what does that mean? Pi. Pi means that we multiply this term that are expressions for from I goes 1 through the n, right? So then you see 1 over sigma times square root 2 pi, this is constant. So we multiply that fraction n times. That's why we got the 1 over sigma square root 2 pi to the nth power. Okay, and then we multiply that exponential term n times for each the different index, different value of index I, right? I goes 1, 2, 3 through the n, right? But the the product of the exponential term, if they have the same base, that we can combine them. Okay, and then the exponent is going to be sum of that the sum of the exponent, right? So that's why we got this. Okay, by the way, so you see here 1 over 2 sigma square. I mean, think about this. Actually, from here to here in the process, we got the sigma I goes 1 through the n. I'm talking about the exponent in the exponential term. Okay, so xi minus mu square over and then 2 sigma square, right? So now see 1 over 2 sigma square is constant, right? So 1 over 2 sigma is a constant, we can bring it out. Right? So I forgot the negative sign right there. So I'll bring out the negative 1 over 2 sigma square. So this is equal to negative 1 over 2 times sigma square. Okay, and then sigma, and the I goes 1 through the n, and then xi minus mu, okay, mu square over, and then 2, just my xi minus mu square, right? Sorry. So we got this. Now we're gonna do the goal. Once we figure out the likelihood function, we have to find out the critical value, right? So to find the critical value, so it's hard to find the critical value. I mean, it's hard to find out the critical value because it's hard to find out the derivative of the L, right? So we're gonna find out what the the critical value of natural log of that likelihood functions. That was strategy. So we just keep using that strategy, right? So now then the natural log, see, natural log L of mu sigma square. It's gonna be we take a natural log this one, then see that fraction times exponential term that can be separated, right? So negative, by the way. So give me a second. Yeah, so natural log of 1 over sigma square root 2 pi to the nth power. Okay, and then plus what? Natural log, right? And the e to the minus 1 over 2 sigma square. And then sigma I equals 1 through the n, and then xi minus mu square. Right. Okay, so this is equal to, now we see, give me a second. First one, this one. So I want to express that fraction without a square root. Okay, so from here, 1 over sigma square root 2 pi, this is equal to, okay, so 1 the square root of 1 over sigma squared times 2 pi, isn't it? Okay, so now that is equal to 1 over 2 pi sigma squared over sigma squared 2 pi, it doesn't matter. So let me write down 2 pi times sigma squared to the 1/2. Okay, all right. So we're gonna plug in this one. I mean, replace the 1 over sigma times square root 2 pi with 1 over 2 pi sigma squared to the 1/2. Then what happened? We're gonna get this natural log, and then 1 over 2 pi sigma squared to the n over 2, right? Okay, and a plus. So let's look at this. We can, bring that term exponent out of the natural log. Okay, so we got, should not plus, right? Not plus, but minus 1 over 2 sigma square, and then sigma I equals 1 summation. Okay, I equals 1 through n, xi minus mu square, and then natural log e. But we know that natural log e is 1. Okay, so it's a little complicated, right? So listen carefully. Okay, so now then natural log, finally we got this natural L of mu comma sigma square is equal to what? N over 2, and then natural log 1 over 2 pi sigma square. Okay, I know this is out of focus, right? So let me finish, write it down, and then I'll fix it. And then minus 1 over 2 sigma square, and then sigma I equals 1 through the n, and then xi minus mu square. Okay, so now then this is equal to, yeah, that's it. I think, can we simplify more? I think, yeah, that's it. So now, yeah, what are we gonna do? We're gonna take a derivative. Take a derivative with what? With respect to mu and sigma. Okay, so sigma square. Okay, so now then, let's see. So now we take a derivative, partial derivative, right? Partial natural n L. Okay, with respect mu. Okay, so it's partial natural L over partial mu. Okay, so that is equal to, let's see, taking the derivative, partial derivative with respect mu, then what? This first term just gone, right? Because the first term is not involved the mu. Okay, give me a second. Okay, so since partial the mu is not involved in the first term, just the first term just gone. When you take a partial derivative of actual L with respect to mu. Now the first second term, we're gonna get what? It's gonna be minus 1 over 2 sigma square, and then summation I equals 1 through the n, and then partial. Here, this we take a derivative. This guy with respect mu. That's not partial, actually d dx d mu, right? And then xi minus mu square. Okay. So now then that is equal to negative 1 over 2 times sigma square, and then summation I equals 1 through the n, and then 2 times xi minus mu, and then times negative. So guys, this is applied to what? The chain rule. Okay, applying chain rule, we got this. So that is equal to, there's a negative 1 and the negative sign, combine them, we're going to get positive. So we got 1 over, and then 2, 1/2 cancel them out, so we got sigma square, and the summation I equals 1 through the n, and then xi minus mu. Okay. So what? We want to find out critical value, right? So we set what? 1 over sigma square times summation I equals 1 through the n, and then xi minus mu is equal to what? 0. Okay. So yeah, I think we see xi or simple data, right? Xi simple data is given in problems, and then mu and sigma square, that's unknown, right? So just leave it. Okay, so we need to get the one more equation for mu and sigma square. So now the second one we take to get the second condition, the information for mu and sigma square. We will take a natural partial derivative. We take a partial derivative of the natural L with respect to the sigma square. Okay. Then what? The that is equal to, you see that right there? We need to take a derivative. Excuse me. We need to take a derivative of what? The first term with respect to sigma square. So then derivative of natural log is what? 1 over that fraction, right? Which is 2 pi sigma square, right? And then times the derivative of the what? The bottom one, which is pi sigma. Okay. So here, the natural log, partial derivative of natural L with respect to sigma square is going to be what? The n over 2 times the sigma square of natural log, right? And then 1 over 2 pi sigma square, okay? And then minus, and then sigma, okay? I mean d sigma square, 1 over 2 times sigma square, and then sigma I equals 1 to n, I equals 1 to n, and then xi minus mu square. Okay, so now then, this is make it understand that, understood that. You see here, we since what actually, yeah, so n over 2 is not involved sigma square, so we just leave it. Okay, and then we take a derivative of that natural log with respect to sigma square. Same thing here, the summation is not involved in sigma square, so we leave it. Okay, and then we take a derivative of that fraction with respect to sigma square. So now then, this is equal to what? There. Okay, so now that is equal to n over 2. Okay, by the way, what's the natural log of f over derivative of the natural f of x? That's going to be f over f prime, right? Given this. Okay, so now we're going to do this. What? The f of x, which is the 1 over, oh, sorry, f prime, right? F prime of f, sorry. So derivative of 1 over 2 pi square with respect to sigma square. Okay, so that is the 1 over times sigma. Okay, sigma. Yeah, oh, I'm sorry, not sigma, right? I'm sorry, n over 2, and then we got the 1 over f prime. F prime going to be what? The 2 pi, right? So 2 pi. And then 2 pi sigma square. Now the plus. Okay. So now plus 1 over. And then see, um, here, when you take a derivative with respect to sigma square, we're going to get the plus the negative sign. We're going to get one more negative sign. And then 1 over, and then what? 2 times sigma to the fourth power. Okay. So what, how, I mean, yeah, so negative, okay. So, I mean, negative 1 over 2 sigma square. See, the prime derivative is equal to 2 sigma square to negative, a negative square. Oops. Okay, times 2. Where 2 comes from? Did you understand that? Now this is equal to what? So we got 4 in the bottom, and then sigma to the first power, and the top one going to be 2. So which is what? 1 over 2 times sigma to the first power. Is it? Okay, so I gave a little bit time to, to think about, this one. So keep in mind this. So now the plus, so we got 1 over 2 sigma to the fourth power, and the sigma I was 1 to the n, xi minus mu. Okay, xi and then minus mu square. Okay, so now we set this one is equal to 0. Okay. I mean, we set what? 1 over sigma to the sigma square I was 1 second, see, 1 over sigma square I was 1 to the n, xi minus mu equals 0. Okay, so that we got this one from the partial derivative of natural L with respect mu, right? And then now we said what? Partial derivative of natural L with respect to sigma square going to be minus, okay, I mean n over 2, actually minus this. Yeah, I was forgot the negative sign right there. I'm sorry. Okay. So the 2, I mean, n over, right, 2 sigma square, the plus 1 over 2 times sigma to the fourth power. Okay. This sigma I equals 1 to root n xi minus mu. Okay. Square. Oops. Square. Okay. Equals 0. So now look at this. 1 over, sigma xi minus mu equals 0. It means that what? Since the 1 over sigma squared is sigma squared always greater than 0, right? Okay. So then that summation must be 0. Okay. So now then this one, the sigma I was 1 through the n. I mean, that is equal to 0. This equation can be reduced by sigma and then xi minus mu equals 0. But we know that we can separate that sigma, right? Because this summation says by linearity. This one is equal to I equals 1 through the n and then xi minus the summation I equals 1 to the n, and mu is equal to 0. Right? So it means that what? It means that sigma I equals 1 to the n xi is equal to summation I equals 1 to the n mu. Okay. Well, we know that what? The sum of all the data, sample data, this is equal to what? N times what? X bar, right? Okay. So that is equal to n times x bar, sample mean, right? So of course the sample mean is 1 over n times the summation of the xi, right? So then this one is what? Just adding summation of mu from I equals 1 to the n. This is going to be n times mu, right? Okay. So n cancel them out. So we got mu equals x bar. So now we can say mu hat is equal to x bar. Mu hat means the what? Maximum likelihood estimator. Okay. So now next one, from the this one here, from that equation, see this equation. Okay. So we got negative, right? So n over 2 sigma square, and then plus 1 over 2 times sigma to the fourth power, and then sigma, summation I equals 1 to the n, and then xi minus mu square is equal to 0. So here, yeah, to, make all the fraction to the non-fraction form, we're going to multiply by 2 times sigma to the fourth power. Then what we're going to get? Negative n times sigma to the square plus, and the summation I equals 1 to the n, and the xi minus mu square is equal to 0. Then, yeah, we solve this equation for sigma square because we want to find out what? We want to express a sigma square in terms of the sample statistics. Okay, so now sigma square is equal to 1 over n. Okay, and then sigma I equals 1 to the n, and the xi minus mu square. So see, this is the what? Actually, the we're gonna say mu. What is mu? We don't know mu, right? So we're gonna replace mu by what? Sample mean x bar. Okay, to fully express the parameter sigma square in terms of the sample statistic. Okay, so now like this, it's similar to the sample variance, but not divided by n minus 1, but divided by n. So here sigma hat square is equal to 1 over n times, and the summation I was 1 to the n, and the xi minus x bar square. Okay, all right. So the now, so please look at the properties of the maximum likelihood estimator in the text, the lecture note. Okay, so Emily, what they are is this: Emily produces estimator with good statistical properties under very general and not restrictive conditions when sample size n is large, and if theta hat, which is the maximum likelihood estimator. Okay, so if theta is maximally likelihood estimator of theta, then what? The MLE, maximum likelihood estimator, are going to be approximately unbiased estimator for theta. It means that the what? Expected value of the MLE is equal to theta, approximately. Okay, and the variance of the MLE is nearly as small as the the variance that could be obtained with any other estimator. Okay, so and then theta hat, which is MLE, it has an approximate normal distribution. Okay, so now next time I'm going to cover the Bayesian estimation of parameters, 7.4.3. Okay, so let me stop here.